top-down fabrication of atomic patterns in twisted bilayer graphene. This manuscript was published in the journal Advanced Materials in 2023. Atomic scale engineering typically involves bottom-up approaches, leveraging parameters such as temperature, partial pressures, and chemical affinity to promote the spontaneous arrangement of atoms. These parameters are applied globally across the entire substrate, resulting in atomic scale features scattered probabilistically throughout the material. In a top-down approach, different regions of the material are exposed to different parameters, resulting in structural changes varying on the scale of the resolution. In this work, we combine the application of global and local parameters in an aberration-corrected scanning transmission electron microscope, or STEM, to demonstrate atomic scale precision patterning of atoms in twisted bilayer graphene. In previous experiments, we showed that many different elements could be inserted into a graphene lattice using a top-down approach. In this approach, the electron beam was used to first damage the graphene and then sputter source atoms from a nearby nanoparticle. These sputtered atoms could diffuse across the graphene surface and bind to the damaged lattice locations. In this way, many different kinds of impurity atoms could be inserted into the graphene lattice. However, this approach was limited to regions very close to the parent nanoparticles from which the impurity atoms were sourced, and the electron beam had to serve two roles, which could not be performed simultaneously, both damaging the lattice and sputtering source atoms. In a subsequent study, tin atoms were able to be directly written into a single layer of graphene at high temperature. In that work, the tin atoms were induced to spontaneously diffuse along a graphene step edge through thermal excitation and supply the requisite source atoms without requiring any action by the beam. That demonstration was confined to start at the step edge where the mobile tin atoms were located. In this work, we tuned the environment to produce diffusing copper atoms across the entire sample surface and show that we can attach these atoms to twisted bilayer graphene wherever we like. This process was automated, and we were able to pattern arrays of atoms and atomic clusters into the graphene with limited human interaction. We began by transferring bilayer graphene onto a protochip's heating chip. Chromium metal was then evaporated onto the surface with an e-beam evaporator. Then the sample was heated in the microscope to promote the evaporation of the chromium and the diffusion of these atoms across the sample surface. Here's an overview image of the sample. The dark areas are the twisted bilayer graphene. The green areas are the chromium nanoparticles, and the white spheres were found to be spurious copper nanoparticles, which ended up playing the leading role in this investigation. To automate the patterning process, we used a custom-built data acquisition and control platform that interfaces with the microscope scan coils and detector output, and performs data analysis on the fly to facilitate real-time feedback control. We used primarily two patterns, an array and a circle, and when attempting to insert a dopant atom, the beam was scanned in a small spiral around the desired location. This generates a small updating image that can be monitored in real time to obtain information about the sample state. We tracked the mean intensity of the spiral image through time. A portion of a dataset is shown here. When a dopant atom is successfully inserted, the mean intensity of the spiral image increases, and when a hole is formed, the mean intensity drops off. By setting two adjustable thresholds, we could determine when one of these outcomes occurred and advance the beam to the next location in the pattern. With the sample held at around 1000 degrees centigrade, we were able to begin patterning atoms into the twisted bilayer graphene. Here's an example of a patterned circle, and an example of a patterned array. We expected these atoms to be chromium because that is what we evaporated across the sample, but it turns out that the vast majority of them were copper. Here's a higher resolution image of the twisted bilayer graphene where we have examples of chromium, copper, and silicon atoms attached to the lattice. We can directly see the difference in this imaging mode based on the brightness of the atoms. Average intensity profiles are given in the inset. As we varied the temperature, we could change the statistical result of the outcome. Here, a hole was denoted as 0, and a dopant was denoted as 1, and we plot the mean outcome as the bar height. At lower temperatures, we obtained mostly holes, and at higher temperatures we switched to mostly inserting dopants. This change happens at about the melting temperature of bulk copper, which suggests that the melting of the precursor material plays a significant role in the outcome, and is consistent with the observation that most of the inserted atoms were copper and not chromium. Chromium has a much higher melting temperature. The final aspect of this study concerns the role of vacancy diffusion. We can see in these patterns that the array is not perfectly formed, and we know that the mechanism for attachment of the dopant atoms is the creation of vacancies in the lattice, which gives the diffusing atoms a chemically reactive attachment point in the substrate. In previous experiments, we showed that vacancies in single-layer graphene diffuse very rapidly away from the irradiated location at high temperatures and coalesce to form defect chains elsewhere in the lattice. Here we performed molecular dynamics simulations to illustrate that vacancy motion is suppressed in the bilayer graphene. Here are some of the results at different temperatures. The blue dots mark the observed position of a single vacancy, and we are comparing single-layer graphene to bilayer graphene. The main takeaway is that for single-layer graphene, as we increase the temperature, the vacancy occupies more and more different lattice sites during the simulation. It's diffusing around a lot, while for the bilayer, the vacancy is more strongly fixed in place. This is not to say that no vacancy diffusion occurs. Indeed, if we perform an analysis of different positions within the arrays, we find that the more neighbors a position has, the faster we obtain an outcome. This is easily understood by invoking the effects of vacancy diffusion. These results show how an atomic scale patterning procedure can be established using a scanning transmission electron microscope as a manipulation platform. In particular, we found environmental parameters that facilitated a bottom-up chemical reaction to a top-down alteration of the substrate. This combined bottom-up and top-down approach allowed the patterning of copper atoms anywhere we desired. Links to the publication may be found in the comment section below.